class.
Thank you, sir.
So, have you gone for any of your TMA?
TMA?
Yes.
They closed it recently. I think they opened it today, so I've not really finished it. Not started it yet.
Okay. No, not to waste time. Let's just go to what we have today. Can you hear me?
Yes, sir.
So, today we'll be looking at what was our last topic that we checked?
Holography.
Holography. So, and last week we said we'll look at what? Because I remember I mentioned
Optical fibers.
optic fibers. Good. That means that's still yeah following the class. I guess this is our 6th meeting, so invariably we have about 2 classes left. So without wasting much time, let's go to the class. Can you see the screen now? Can you see what I'm displaying on
Yes,
the
sir.
screen?
Yes.
Okay, optic fiber. Intended learning outcomes. We'll be looking at optic fibers today. Intended learning outcomes. We said at this end of this lesson, we should be able to explain light transmission through fiber, distinguish between step index and gradient index fibers, derive expression for pulse dispersion in fibers, and solve simple problems on optical fibers. So let's go straight to the class. Said an optic fiber consists of a cylindrical glass core. Can you see that glass core? A cylindrical glass core. Hello?
Yes, sir. Yes, sir. I can
Cylindrical
see.
glass core surrounded by a transparent cladding of lower refractive index. We now say that this assembly is further covered by a plastic coating to protect it against chemical attack, mechanical impact, and other handling damages. This is the coating we're talking about. So the core, the cladding, and the coating, that makes up the optical fiber. Okay. So the figure update that I just showed you now shows the geometry of a typical optic fiber. The core diameter is in the range of 5 micrometer to 125 micrometer, with the cladding diameter usually in the range of 100 micrometer to 150 micrometer. That means it's smaller than millimeters. The plating coating diameter is around 250. Can you see each of those coatings now? If you just segments now, they are telling you the dimension. Now, please, can you just give me a minute? Let me attend to something. Sorry for that short break in transmission. Abdulaziz Abdusalam, you're welcome. John Daniels, can you hear me?
Yes, sir.
Okay. I'm trying to put on the power so that we won't have a break. So, but I'm having issues with that. But let's continue. I don't want this laptop. If it goes off, please just reconnect. Is that clear? Hello? Hello?
Yes.
If it goes off, please just give
Yes, sir.
me
Yes, sir.
just give me 2 minutes. I will reconnect. So let me just continue. So we've seen the diameter of the optic fiber. Abi, I think I've said that. I said the core diameter is in the range 5 micrometer to 125. The cladding 100 micro to 150. Then the plastic coating is 250 micrometer. Now, in order to understand why the incoming light does not come out through the cylindrical surface of the fiber, you should recall the phenomenon of total internal reflection. Now, okay, when light travels from an optically denser medium to a less dense medium, it bends away from the normal, as shown in figure above. I will soon show you the figure. I'll bring up the figure now. If the refractive index of the two media are N2, N1, N2 such that N1 is greater than N2, and phi1, phi2 are the angles of incidence and the angles of refraction respectively, then from Snell's law, and refractive index of 1 again over that of 2 equals to sine theta 1 over sine theta 2. What do we mean by that? Okay, let me bring this up. Okay, look at this. Now, when you have a light traveling, or that is touching a plane surface, now a part of it is reflected. Hello, can you hear me? Hello?
Yes, sir.
Now, a part of it is, this is the incident. Look at it. Look at this incidence. Now, look at this arrow. This light goes in here. A part of it is reflected, while a part of it is what? Is refracted. But at a particular angle of incidence, we don't experience what we call refraction. We don't experience what we call refraction. What we have is a reflection. To give us a reflection. Now you can see here that this reflection here, this refraction here is no longer there. Is that not so? It is parallel, it is at 90 degrees. Is that not so? That means we have total internal reflection. And any angle above that will give you total internal reflection. The minimum angle that we're talking about is the critical angle. This angle here is the critical angle whereby there is no, that the what's it called? The reflection is 90 degrees, and anything apart from that, we have what we call total internal reflection. This is not partial. What we have here is partial. So it is total internal reflection. And the condition is that for that is that light must travel from a dense medium to a less dense medium. That means from, let's say, water to air. Is that clear? Normally, refraction that we talk about is from air to water or air to glass, but it can travel from air, from water to air, or from glass to air. So that is what we are talking about now. Now let's look at the illustration. The illustration says that as the angle of incidence increased, the refracted ray will further bend away from the normal ultimately until when the angle of incidence reaches the critical value theta subscript c. The refracted ray travel along the interface separating the two media, as shown in figure 2b. Can you see that's 2b here? The 2b here. Can you see this angle here? The angle of refraction here is what? 90 degrees. So you have total internal reflection. So we now say that when the angle of incidence increases beyond Q of C, there is no refracted ray. If it increases beyond this 2b, the 2b that I showed here, there is no refracted ray, and the incidence ray undergoes total internal reflection into the optical denser medium. The phenomenon is called total internal reflection and the critical angle. So I want you to, as an assignment, write a short note on total internal reflection and critical angle. It should come out in your exam. If I'm your examiner, if I'm the one to set your questions, that should come out. Hello, can you hear me?
Yes, sir. Yes, sir.
Good. So we said type of fibers. We said, as mentioned before, in the simplest form, an optic fiber consists of a glass core and a cladding, also of glass, of lower refractive index. So we have two types of optical fibers. We have step index fiber. We now say that this type of fiber is that in which there's a sudden change in the refractive index at the core cladding interface. Let's look at the core cladding interface. Look at what we're talking about. This is the core cladding interface. This is the core cladding. There's what? So the total internal reflection, the refractive index changes at the core cladding interface at this point. And on the other hand, in the other one, which is the gradient index fiber, the refractive index decrease continuously from the core axis. So this is the core axis. So what we are saying is that from the first one we described here, refractive index decreases at the core cladding interface here. But if for the gradient interface, it decreases at the core interface over there. So that's what we are talking about. So we said there's a sudden change in the refractive index at the core cladding interface, and it's called the step index fiber. The variation of the refractive index with the radius of such fiber is shown in figure 3. That's what I just showed you. That's this. It's coming up. That is this one. Then furthermore, when light travels through optical fiber, there are different types of losses as well as a broadening of the pulses. This aspect of fiber of vital importance for communication. Now, if you note what I put in bracket here, I said in optical communication, signal is transmitted through the fiber in the form of pulses. Can you see? In optical communication, signal is transmitted through the fiber in the form of what? In the form of pulses. Now, what we mean is that we said when light travels through optical fiber, there are different types of losses. We still go back to inside the material, as well as a broadening of the pulses. Now, this aspect of optical fiber a vital importance of optical communication. That is why they use optic fiber cable, so that there will be no losses of signal. There will be no loss of pulses. You can use some other wires or cables, but there's always a loss of what? Pulses, which is a signal, which is a signal that optical fiber carry, which is used in optical communication. That's why what all these MTN and Glo, if it is the pulses that transmit within those cables. But if you use a normal cable, there will be losses, there will be power losses. But if you use an optical fiber cable, there will be minimal losses. That's what we are trying to talk about. There will be minimal losses in terms of pulse transmission. I think you get what I'm trying to say.
Yes, sir.
Good, good. So I have the last slide there that says that application of optical fibers. We said in the transmission of light, an example of that is fiber scopes, which is used extensively in medicine and engineering. And that makes it possible to inspect the cavity in the human body and look inside the heart while it beats. And it's also used in communication. So I want us to quickly look at the course material itself. Let me unshare this and open the course material so that you will see what we're talking about. Because these are just summary. I just have to pick a few. Is that clear? You still have a lot of things to read up and bring to our WhatsApp group for deliberation for anyone that you don't seem to understand. Abdulaziz, can you hear me? Are you still there?
I'm with you, sir.
Okay, good. So I'm to share the course material now. I will show you where I've been taking some of the readings from. We're almost done with the material itself. I'm coming. And it is strongly advised that you go through all the questions in this material. So we'll be talking about optical fibers. So we've talked about this. We've talked about this. I've showed you this. And I've explained a little bit. So what they just did here was to make, to find the angle theta of C, which is arc sine N2 over N1. So whatever you will find, you know how to do this. A good student of mathematics should do this. So it is important that you go through all this. Light propagating through a fiber through by total internal reflection. Total internal reflection. Can you see? As light is moving, it is transmitted by total internal reflection. There is no refraction. It just simply what's it called? So as you can see the core, you can see the cladding. You can see it's strictly by total internal reflection. So you should read what is called, what's an optical waveguide. Can you see? Hello? Please note, hello, can you hear me? Please note this, optical waveguide. What does it mean? Those are the questions that can be asked. So you should also look at all this. They are self-explanatory. That's why I didn't bring it into the slide. So the types of fly fiber, I've talked about it. I've talked about the core, the refractive index profile of a step index fiber. And this is the gradient index fiber. So you should go through it, understand what it means. And if you have to draw, if I ask to draw, just memorize it. And now there's a question here. So what will happen if the refractive index of the cladding material is higher than that of the core? Please note that the answers are at the back there. So application of optical fibers said is the transmission of images using optical fiber is in the flexible fiber scope. So that is what is used. You should read that extensively. And optical communication through fibers, I've mentioned that briefly in the material. So next week, we'll start our class from which is probably the last class, from optical pulse dispersion in fibers. I think that's what you should start. That will be our last. No, I think we'll stop here. We'll start from optical communication through fiber. I think I will need to dwell more on this. So if you have to read, you have to read up to this point. Can you get me? Do you get me? To cover, hello? Hello? Are you still there? I want a response, please. So next week, we will talk about optical communications through fiber. Optical communication through fiber. Hello, can you hear me? So that will be on page 72. So this is what we look at next week. Let's look at the summary and the questions. Are you there?
Yes, sir.
Okay. Did you get what I said?
No, sir. I
said that you have to read up to page 72. This is where I stop. For our last class, I will be treating optical communications through fiber. You know, we just talked generally about optical fibers today. So you read up to this point, limit here. So optical fibers, optical communications through fiber. We want to really deal with optical communication, the communication aspect of optical fiber. That's what we're going to look at next week, which will be our last topic. Then the upper week will be revision. But there might be a situation whereby if we are asked to round off the class next week, we have two sessions. We have our normal class 5 to 6. Then we have the last class 8 to 9 in the evening. Do you understand?
Yes, sir.
If you're asked to round up next week to make it 8 weeks, we will have a normal class 5 to 6, then 8 to 9. But if there's nothing like that, we will still have today, next week, and upper week, making 3 sessions. So let's go to the questions that we have. Let's go to the questions that we have here. And all those SAQ1, you know, there was a question that was asked earlier. SAQ1 and SAQ2. Let's see the answers here, if they are there. Okay. So suppose you have 2 optical fibers A and B. The refractive index of the core and the cladding are this.